Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to let your thoughts drift weightlessly into the vast corridors of cosmic mystery. This is your moment to leave behind the weight of the day and step quietly into a question that has haunted humanity since the first eyes turned skyward. What is the actual size of the universe? If you enjoy these quiet journeys through space and time, a like and subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen, breathe, and let wonder carry you gently toward rest. There is a photon of light arriving at Earth tonight that began its journey long before humans existed. It left a distant galaxy when the universe was young, when stars were just beginning to gather into the patterns we now recognize. For 13 billion years, it travelled through the expanding darkness of space, crossing distances so vast that even speaking them aloud feels like trying to count grains of sand on every beach that has ever existed. Tonight, that ancient light will touch a telescope mirror somewhere on Earth, and in that instant, a piece of the early universe will whisper its story to us. This is not fiction. This is the reality of looking outward into space. Every telescope is a time machine. Every photon carries history. When astronomers measure the light from distant galaxies, they are not seeing those galaxies as they are now, but as they were billions of years ago. The farther away something is, the older its image becomes. Light takes time to travel, and the universe is so immense that time and distance become inseparable. To ask how large the universe is means also asking how old it is, how far light has travelled, and what lies beyond the edge of what we can see. The idea that a single particle of light could journey for billions of years seems impossible until you begin to understand the scale involved. A light year, the distance light travels in 1 year, is nearly 10 trillion kilometres. Multiply that by billions, and you have distances that defy ordinary comprehension. Yet this is the stage on which the universe unfolds. Galaxies separated by billions of light years, clusters of galaxies forming webs across hundreds of millions of light years, and beyond all of that, perhaps an infinite expanse we will never see. The question of the universe's size is not new. Humans have always looked up and wondered. Ancient peoples saw the stars and imagined them as holes in a celestial dome, as campfires of the gods, as distant suns like our own. They measured what they could with the tools they had, crude by modern standards, but driven by the same curiosity that drives us today. Each generation built on the work of the last, slowly expanding the boundary of the known, pushing the horizon of measurement farther and farther until it reached beyond galaxies, beyond clusters, to the very edge of the observable universe itself. What makes this journey so compelling is that it mirrors the journey of a single human life. We begin small, aware only of our immediate surroundings. Slowly, we expand our understanding, learning about the world, then the planet, then the solar system, and eventually the cosmos. Each step requires letting go of old certainties and embracing larger truths. Each expansion of scale humbles us and yet also elevates us, because to understand the universe is to understand our place within it. Tonight, as you settle into stillness, imagine that photon of light arriving. Imagine it passing through the cold vacuum of space, unchanged for eons, carrying within it the signature of a galaxy that may no longer exist in the form it once held. Imagine all the photons arriving every second from every direction, each one a messenger from a different distance, a different time. The universe speaks to us in light, and by listening carefully, by measuring patiently, we learn its size, its age, its story. This is the impossible beginning, not of the universe, but of our understanding of it. A single photon, crossing billions of years, reminds us that the cosmos is both unimaginably vast and intimately connected to us. That light travelled all this way to be seen, and we are here to see it. That alone is a kind of miracle, a meeting of the infinitely large and the infinitely small, and it is where our journey begins. Long before telescopes, before equations, before anyone understood what stars truly were, there were people who looked at the sky and tried to make sense of it. They did not have the language of light years or galaxies, but they had patience, careful observation, and an unshakable belief that the heavens could be understood. In the ancient city of Babylon, nearly 4,000 years ago, astronomers kept detailed records of the movements of planets and stars. They tracked the rising and setting of Venus, noted the positions of Jupiter and Saturn, and predicted eclipses with surprising accuracy. These early sky watchers were not trying to measure the size of the universe in the way we think of it today. They were trying to understand the patterns they saw, to predict what would come next, to find order in what seemed like chaos. But in doing so, they laid the foundation for everything that followed. They showed that the sky was not random, that it moved in cycles, that it could be studied and mapped. They proved that human reason could reach beyond the earth and touch the heavens, even if only in small ways. The Babylonians were not alone. In Egypt, priests used the stars to align the pyramids with astonishing precision. In China, astronomers recorded supernovae and comets centuries before such events were documented elsewhere. In India, mathematicians developed sophisticated models of planetary motion. Across the world, in cultures that never spoke to one another, the same impulse arose, to look up and ask how far, how many, how large. That impulse, more than any single discovery, is what began the long journey toward measuring the universe. The tools were simple: a stick in the ground to cast a shadow, a circle marked on stone to track the sun's path. The naked eye, patient and steady, watching the same patch of sky, night after night. These were not powerful instruments, but they were enough. Enough to notice that the stars moved in predictable ways. Enough to see that some lights in the sky wandered while others stayed fixed. Enough to realize that the Earth itself might not be the center of everything. One of the earliest breakthroughs came from understanding the Earth itself. Before anyone could measure the distance to the stars, they had to measure the ground beneath their feet. The realization that the Earth was round, not flat, was a profound shift in perspective. It meant that the horizon was not the edge of the world, but simply the limit of sight. It meant that the surface curved away in all directions, that travellers could sail west and eventually return from the east. It meant that the Earth was a sphere suspended in space, and if it was a sphere, then it had a size that could be measured. This was where it all began, not with the stars, but with the Earth. Ancient thinkers realized that if they could measure the size of the planet, they might begin to understand the scale of everything beyond it. They noticed that at noon on the summer solstice, the sun shone directly overhead in some cities but cast shadows in others. They measured the angles of those shadows, calculated the distances between cities, and used geometry to estimate the circumference of the Earth. The numbers they arrived at were remarkably close to what we know today, achieved with nothing more than sunlight, shadows, and human ingenuity. That achievement was more than a measurement. It was a statement of intent. It said that the universe, no matter how vast, could be studied, that numbers could describe the world, that reason could unlock mysteries that seemed beyond reach. It set the stage for everything that followed, for the measurement of the moon's distance, the sun's size, the space between stars, and eventually the immensity of galaxies and the observable universe itself. Where it all began was not in a laboratory or a university. It was in the open air, under the sky, with people who had nothing but curiosity and determination. They did not know they were beginning a journey that would stretch across millennia and eventually measure billions of light years. They only knew that the heavens called to them, and they answered with careful observation, patient calculation, and the belief that understanding was possible. That belief, more than any tool or technique, is what made everything else possible. In the 3rd century before our era, in the city of Alexandria, a man named Eratosthenes made a discovery that would echo through the centuries. He was a scholar, a librarian, a mathematician, someone who spent his days among scrolls and his nights pondering the movements of the heavens. He had heard a curious fact that in the city of Syene, far to the south, the sun shone directly overhead at noon on the summer solstice. Wells were illuminated all the way to the bottom. Vertical sticks cast no shadow. The sun was perfectly vertical, but in Alexandria, where Eratosthenes lived, the sun was never quite overhead. Even at noon on the solstice, it cast a shadow. This small difference captured his attention. If the earth were flat, as many believed, then the sun should appear at the same angle everywhere. But if the earth were curved, if it were a sphere, then the angle of the sun would change depending on where you stood. The shadow in Alexandria was proof of curvature, evidence that the surface of the planet bent away from the vertical. Eratosthenes saw an opportunity. If he could measure the angle of the shadow in Alexandria, and if he knew the distance between Alexandria and Syene, he could calculate the circumference of the entire Earth. It was a bold idea, audacious in its simplicity. He did not need to travel the world. He did not need elaborate instruments. He needed only a stick, a shadow, and some careful geometry. On the summer solstice, he measured the angle of the shadow cast by a vertical pole in Alexandria. It was about 7 degrees, a small but measurable slant. He knew that Syene was roughly 5,000 stadia away, a unit of distance used at the time. If 7 degrees corresponded to 5,000 stadia, then the full circle, 360 degrees, would correspond to a much larger distance. He did the calculation and arrived at a number. The circumference of the Earth was approximately 250,000 stadia. Converting ancient units to modern measurements is imprecise, but most scholars agree that Eratosthenes' result was within a few percent of the true value. He had measured the size of the Earth using nothing more than sunlight and reasoning. It was one of the great intellectual achievements of the ancient world, a demonstration that nature could be understood through observation and mathematics. But the significance of this discovery went far beyond the number itself. It proved that the Earth was large, far larger than the lands people knew. It suggested that the planet was not the flat expanse of myth but a sphere hanging in space. And it opened the door to a much larger question. If the Earth could be measured, what about the moon, the sun, the stars? If geometry could reveal the size of the planet, could it also reveal the distances to the heavens? Eratosthenes did not stop with the Earth. He turned his attention to the moon, trying to estimate its distance by observing lunar eclipses. He studied the writings of earlier astronomers, built on their work, and contributed to a growing body of knowledge about the cosmos. His methods were not perfect, but they were rigorous. He understood that measurement required precision, that small errors could compound, and that the pursuit of truth demanded patience and care. What makes this discovery so powerful is not just the result, but the approach. Eratosthenes showed that the universe was not beyond human understanding. Mapped. The tools might be simple, the methods crude by modern standards, but the principles were sound. Observation, reasoning, calculation. These were the keys to unlocking the secrets of the cosmos. Standing under the sun in Alexandria, measuring the angle of a shadow, Eratosthenes took the first true step toward measuring the universe. He could not have known how far that journey would go, how the methods he pioneered would eventually reach across billions of light years. But he knew that the question was worth asking, that the effort was worth making, and that the universe, vast as it seemed, was not closed to human inquiry. The discovery was simple in execution but profound in implication. It said that the size of the world could be known, that the heavens were not untouchable mysteries, but part of the same reality we inhabit, that a single person, armed with curiosity and reason, could reach across distances and touch the infinite. That spark of understanding, lit in Alexandria more than 2,000 years ago, still burns today, guiding us as we measure galaxies, clusters, and the observable universe itself. When Eratosthenes announced his measurement, the reaction was not uniform. Some scholars marvelled at the elegance of his method, the way he had turned a simple shadow into a tool for measuring the Earth. Others were sceptical. The number seemed too large, the idea too bold. How could anyone claim to know the size of the entire planet based on observations from just 2 cities? The debate that followed was not just about numbers. It was about whether the world could truly be understood, whether human reason was powerful enough to grasp the scale of reality. This tension between awe and disbelief has always accompanied great discoveries. When something challenges our assumptions, when it expands our sense of scale, the natural response is a mixture of wonder and doubt. We want to believe, but we also want proof. We are drawn to the mystery, but we resist letting go of what we thought we knew. This duality is part of what makes the pursuit of knowledge so compelling. It is not a smooth path, but a winding one, filled with moments of revelation and moments of resistance. Imagine living in a world where most people believed the earth was flat, where the horizon marked the edge of everything, where the sky was a dome close enough to touch. Then imagine someone telling you that the ground beneath your feet curves away in all directions, that the earth is a sphere so large it would take years to walk around, that the stars above are not nearby lights but distant suns. The shift required is not just intellectual but emotional. It means accepting that the world is far larger, far stranger than you ever imagined. For some, this realization brought a sense of liberation. If the earth was so vast, what else might be true? If geometry could reveal such truths, what other secrets might mathematics unlock? The mind that accepts one expansion of scale becomes ready for the next. From the size of the earth to the distance of the moon, from the moon to the sun to the stars, each step builds on the last. Each measurement prepares the ground for the next leap outward. For others, the expansion of scale was unsettling. It made the familiar world feel smaller, less central, less important. If the earth was just a sphere in space, then perhaps it was not the centre of creation. Perhaps the sun did not revolve around us. Perhaps the stars were not placed for our benefit. These were uncomfortable thoughts, and they met with resistance. Some rejected the measurements outright, clinging to older beliefs. Others accepted the numbers but struggled with what they implied. The human response to cosmic scale is always layered. On one hand, there is awe, the thrill of discovery, the satisfaction of solving a puzzle. On the other hand, there is disbelief, the discomfort of being proven wrong, the fear of insignificance. Both responses are valid. Both are part of the process. Awe without skepticism leads to credulity. Skepticism without openness leads to stagnation. The balance between the two is what allows knowledge to grow. What Eratosthenes and others like him understood was that the pursuit of truth required not just clever methods but also courage. Courage to question accepted beliefs, courage to propose ideas that seemed impossible, courage to stand by their measurements even when others doubted. They were not seeking fame or recognition, though some found it. They were seeking understanding, and they were willing to follow the evidence wherever it led. The disbelief faded slowly. As more measurements were made, as more scholars confirmed the results, the idea of a spherical Earth became widely accepted. But the pattern repeated with each new discovery. When Copernicus suggested the Earth orbited the Sun, he was met with disbelief. When Galileo saw moons orbiting Jupiter, proving that not everything revolved around Earth, he faced resistance. When Edwin Hubble showed that galaxies were moving away from us, that the universe was expanding, many scientists struggled to accept it. Each time, the scale expanded. Each time, awe and disbelief walked hand in hand. Today, we live with the knowledge that the observable universe is 93 billion light-years across, that it contains trillions of galaxies, that it may be infinite beyond what we can see. These ideas no longer provoke the same visceral disbelief they once might have, but only because generations of scientists built the case slowly, measurement by measurement. The awe remains. Standing under the night sky, knowing what we now know, it is impossible not to feel the weight of it, the staggering immensity, the profound mystery. Awe and disbelief are not opposites. They are companions on the journey toward understanding. Awe opens the mind. Disbelief sharpens it. Together, they drive us forward, pushing us to ask better questions, to seek stronger evidence, to expand our sense of what is possible. The reaction to Eratosthenes' measurement was the beginning of a pattern that continues today, a pattern of wonder and doubt, of resistance and acceptance, of minds stretching to hold truths larger than themselves. Once humanity accepted that the Earth was round and measurable, the next natural step was to turn that same curiosity outward, toward the sky. If the ground beneath our feet had a size, what about the moon, the sun, the stars? But here, the methods that worked so well for Earth ran into a problem. The stars, no matter how carefully observed, appeared as mere points of light. They showed no visible size, no angle, no measurable width. They seemed fixed against the sky, unchanging from night to night, year to year. And yet, if they were truly distant suns, as some suspected, they must be impossibly far away. This created a paradox. If the stars were close, as many believed, then they should show some measurable change in position as the Earth moved. Just as your finger seems to shift against the background when you close one eye and then the other, so too should a nearby star shift against more distant stars as the Earth orbits the Sun. This shift is called parallax, and it is one of the most powerful tools for measuring distance. But no matter how carefully astronomers looked, they could not detect it. The absence of parallax led to two possible conclusions. Either the Earth did not move, which supported the geocentric model placing Earth at the centre of the universe, or the stars were so far away that their parallax was too small to measure with the instruments available. Both possibilities seemed extreme. If Earth did not move, then it was the centre of everything, which appealed to human vanity but created complex explanations for planetary motion. If the stars were truly that distant, then the universe was far larger than anyone had dared to imagine. This contradiction troubled astronomers for centuries. The technology to measure tiny angles simply did not exist. Telescopes improved slowly, instruments became more precise, but the parallax of even the nearest stars remained stubbornly beyond reach. Some took this as proof that Earth was stationary. Others insisted that the lack of parallax only proved the stars were farther than expected. Not that the heliocentric model was wrong. The debate was not just about measurement, but about worldview, about humanity's place in the cosmos. The tension between what was observed and what was suspected grew sharper as the heliocentric model gained support. Copernicus had proposed that Earth orbited the Sun, a revolutionary idea that explained planetary motion more elegantly than the old geocentric system. But without parallax, critics could argue that the idea was unproven. If Earth truly moved, where was the evidence in the stars? The contradiction could not be resolved with philosophy alone. It required better tools, more precise measurements, and above all, patience. Generations of astronomers searched for parallax, convinced that it must exist if the Copernican model was correct. They knew that detecting it would be extraordinarily difficult. The angles involved would be tiny, smaller than the width of a coin seen from kilometers away. But the pursuit continued because the alternative was to accept that Earth was the centre of everything, a conclusion that seemed increasingly unlikely as more evidence accumulated. Think about what it must have felt like to search for something you believed was there but could never quite see. To spend years refining instruments, training your eye, recording positions, only to find that the stars refused to reveal their secret. The contradiction hung in the air, unresolved, a question waiting for an answer that technology had not yet provided. It was both frustrating and tantalizing, proof that the universe held mysteries just beyond the edge of human capability. The contradiction also highlighted a deeper truth about science. Progress is not always smooth. Sometimes, the evidence you need does not exist yet. Sometimes, the tools are not precise enough. Sometimes, you have to wait. Building theory and method patiently, trusting that future generations will find what you could not. The astronomers who searched for parallax knew they might never see it themselves, but they laid the groundwork for those who came after. And then, finally, in the 19th century, the contradiction was resolved. Improved telescopes, more stable instruments, and careful observations over many months allowed astronomers to detect the tiny shifts they had been searching for. The stars did show parallax. The angles were minuscule, but they were real. Earth did move. The heliocentric model was correct, and the distances revealed were staggering, far greater than most had dared to believe. The nearest star was light years away. Trillions of kilometers, a gulf so vast that the absence of parallax for so long suddenly made perfect sense. The contradiction had been resolved not by abandoning the question, but by refining the tools. The universe was larger than expected, but it was knowable. The stars were distant, but they were measurable, and the method that revealed their distances, parallax, would become one of the first rungs on the cosmic distance ladder, a technique that would eventually help measure the size of the Milky Way and beyond. The contradiction that troubled so many for so long turned out to be a doorway opening onto scales that redefined everything humanity thought it knew about the cosmos. As astronomers struggled with the contradiction of parallax, a broader debate raged about the nature of the universe itself. Were we at the centre, as tradition and intuition suggested, or were we adrift in a vast expanse, just one world among many? The question was not merely technical. It touched on philosophy, theology, and the human sense of importance. Different thinkers proposed different models, each trying to reconcile observation with belief, mathematics with meaning. The geocentric model, which placed Earth at the centre of the universe, had dominated for more than 1,000 years. It was codified by Ptolemy in the 2nd century, building on earlier Greek astronomy. In this system, the sun, moon, planets, and stars all revolved around a stationary Earth. The model was complex, requiring epicycles, small circles within larger circles, to explain the strange backward motion of planets as seen from Earth. But it worked. At least in the sense that it could predict planetary positions with reasonable accuracy. Supporters of the geocentric model found comfort in it. Earth was special, unique, central. Humanity was not lost in the void but placed at the heart of creation. The heavens moved around us, and every motion had purpose. It was a worldview that aligned with religious teachings and with the intuitive sense that the ground beneath our feet was solid and unmoving. To suggest otherwise was to challenge not just astronomy, but the entire framework of meaning. But there were problems. The geocentric model grew more complicated with each refinement. As observations improved, more epicycles were needed, more adjustments, more layers of complexity. Some astronomers began to wonder if the model was fundamentally flawed, if perhaps the universe was structured differently than tradition claimed. It was in this atmosphere of doubt and questioning that the heliocentric model emerged. Nicolaus Copernicus, a Polish astronomer working in the 16th century, proposed a radical alternative. What if the Sun, not Earth, was at the centre? What if Earth was just another planet, orbiting the Sun along with the others? This simple shift in perspective eliminated much of the complexity of the geocentric model. Planetary retrograde motion, the puzzling backward loops that planets seem to trace, could be explained as an optical illusion caused by Earth overtaking slower outer planets in their orbits. The math became simpler, the motions more elegant. But the heliocentric model faced fierce resistance. It contradicted scripture, at least as interpreted by the Church. It contradicted common sense. How could Earth be moving if we felt no motion? It contradicted observation. Where was the parallax that should appear if Earth orbited the Sun? Copernicus published his work near the end of his life, perhaps aware of the controversy it would provoke. For decades, it remained a minority view, discussed by scholars but not widely accepted. Galileo Galilei, using one of the first telescopes in the early 17th century, found evidence that supported the heliocentric model. He saw moons orbiting Jupiter, proving that not everything revolved around Earth. He saw phases of Venus, showing that Venus must orbit the Sun, not Earth. He saw mountains on the Moon, proving that celestial bodies were not perfect spheres as tradition claimed. Each discovery chipped away at the old worldview, building the case for a new one. Still, the debate continued. Johannes Kepler refined the heliocentric model, showing that planetary orbits were ellipses, not circles, and that planets moved faster when closer to the Sun. His laws of planetary motion were precise, mathematical, and predictive. They worked better than the old epicycles. But even then, many resisted. Change in worldview is slow, especially when it challenges deeply held beliefs. The theories divided astronomers into camps. Some clung to the geocentric model, refining it, defending it, finding ways to explain away new observations. Others embraced the heliocentric view, despite the lack of direct proof like parallax. Still others proposed hybrid models, trying to preserve some aspects of both. The universe became a battleground of ideas, each side marshalling evidence, each trying to convince the others. What makes this period so fascinating is not just the clash of models, but what it reveals about human nature. We cling to familiar ideas even when evidence begins to point elsewhere. We resist change, not out of stubbornness alone, but because changing our view of the cosmos means changing our view of ourselves. To accept that Earth is not the centre is to accept a kind of cosmic humility, to let go of the idea that we are special in position even if we remain special in other ways. Eventually, the heliocentric model prevailed, not because of a single decisive experiment, but because of accumulated evidence, because it explained more with less complexity, because it fit the observations better. The measurement of stellar parallax in the 19th century was the final confirmation, proving beyond doubt that Earth orbited the Sun and that the stars were vastly distant. But by then, the intellectual battle had already been won. The theories had shifted, and with them, humanity's place in the universe. The lesson from this period is that understanding the cosmos requires more than observation. It requires imagination, the willingness to consider ideas that seem impossible, the courage to follow evidence even when it leads to uncomfortable places. The theories that divided astronomers were not just competing explanations, they were competing visions of reality, and the one that survived was the one that matched the universe as it truly is, vast, decentralized, and far stranger than anyone expected. For centuries, the hunt for stellar parallax became an obsession among astronomers. It was not just a technical challenge, but a quest for proof, a way to settle once and for all whether Earth truly moved or whether the old geocentric model still held. The search required patience, precision, and instruments that pushed the limits of what was possible. Many tried and failed. Generations passed without success. But the pursuit continued, driven by the belief that the answer was out there, hidden in the tiny movements of the stars. The problem was deceptively simple. If Earth orbits the Sun, then our position in space changes by hundreds of millions of kilometers over the course of a year. From one side of the orbit to the other, we view the stars from different vantage points. Nearby, stars should appear to shift slightly against the background of more distant stars, creating a measurable angle. This parallax is the same effect you see when you hold your finger up and switch between closing one eye and the other. The finger seems to move. In the same way, nearby stars should seem to move, but the angles involved are minuscule. Even the nearest stars are so far away that their parallax is less than 1 arcsecond, a unit so small that it represents a 6800th of a degree. To put that in perspective, it is like trying to measure the width of a coin from several kilometers away. The challenge was not just seeing the shift, but measuring it accurately enough to be certain it was real and not an artifact of atmospheric distortion, instrument error, or observer bias. Early attempts failed because the tools were not precise enough. Telescopes in the 17th and 18th centuries could see stars clearly, but they could not measure positions with the accuracy required. Atmospheric turbulence blurred the images, temperature changes warped the instruments, human error crept into every measurement. Some astronomers thought they had detected parallax, only to realize later that what they saw was something else. The slight wobble of Earth's axis, the refraction of light through the atmosphere, the imperfections of their equipment. The pursuit became a test of persistence. Astronomers built better telescopes, mounted them on more stable platforms, observed the same stars night after night for months, even years. They developed new techniques to minimize error, comparing the positions of many stars at once, using mathematical methods to filter out noise. They trained themselves to see with extraordinary precision, learning to judge tiny differences in brightness and position that most people would never notice. One of the key figures in this pursuit was Friedrich Wilhelm Bessel, a German astronomer working in the early 19th century. Bessel understood that success required not just a good telescope, but a systematic approach. He chose his target carefully, a star called 61 Cygni, known to have a large, proper motion, the gradual drift of stars across the sky over time. A star with large proper motion was likely to be relatively close, making it a good candidate for parallax. Bessel observed 61 Cygni for more than a year, measuring its position relative to nearby stars hundreds of times. He corrected for atmospheric effects, for the slight shifts caused by Earth's axial wobble, for every source of error he could identify. Slowly, a pattern emerged. The star did shift, not in a straight line as proper motion would suggest, but in a tiny ellipse, a back and forth motion that repeated with the cycle of Earth's orbit. It was parallax. In 1838, Bessel announced his result. 61 Cygni was approximately 10 light-years away, a distance so vast that it took light a decade to cross. For the first time in history, a human being had measured the distance to a star. The heliocentric model was confirmed. Earth did orbit the Sun. The universe was far larger than anyone had imagined. The pursuit that had consumed so many astronomers for so long had finally succeeded. But Bessel was not alone. Around the same time, other astronomers made similar breakthroughs. Friedrich Struve measured the parallax of Vega, and Thomas Henderson measured the parallax of Alpha Centauri. The methods were different, but the conclusions were the same. The stars were light-years away, separated from us by distances that dwarfed the solar system. The cosmos had expanded, not in physical space, but in human understanding. The pursuit of stellar parallax is a story of human determination. It shows what can be achieved when people refuse to give up, when they refine their methods, improve their tools, and keep searching even when success seems distant. It also shows the power of measurement. A single number, the angle of stellar parallax, unlocked a truth that had been hidden for millennia. It proved that the universe was larger, stranger, and more magnificent than tradition suggested. For us, thinking about this pursuit offers a kind of comfort. It reminds us that difficult questions can be answered, that mysteries can be solved, that patience and persistence pay off. The astronomers who searched for parallax did not know if they would succeed. They did not know if the stars were even close enough to measure, but they kept trying, and in the end, they found what they were looking for. That determination, that refusal to accept that something is unknowable, is what drives science forward and what allows us to measure the universe itself. When Friedrich Bessel finally measured the parallax of 61 Cygni, the data he gathered was more than just numbers on a page. It was proof, concrete and undeniable, that the stars were not painted on a celestial sphere but scattered across unimaginable distances. The angle he measured, less than 1 arc-second, translated into a distance of about 10 light-years. 10 years for light to travel, moving at 300,000 kilometers per second. The number was staggering, but it was also precise, derived from careful observation and rigorous calculation. The data did not stand alone. Bessel's measurements were part of a larger pattern emerging in astronomy. As more astronomers refined their techniques and improved their instruments, more stellar distances were measured. Each new measurement added to the picture, revealing that the stars varied enormously in distance. Some, like Alpha Centauri, were relatively close at just over 4 light-years. Others, like Vega and Sirius, were farther. Still others were so distant that their parallax could barely be detected even with the best telescopes of the time. What made these measurements so powerful was their consistency. Different astronomers, using different telescopes in different locations, arrived at similar results for the same stars. This convergence of data built confidence. It showed that the measurements were not flukes but reflections of reality. The stars truly were light-years away, and the method of parallax truly worked. The universe had revealed one of its secrets, and humanity had the tools to decode it. The data also revealed something unexpected. The stars were not evenly distributed. Some regions of the sky had many nearby stars, while others had none. The distances varied wildly, from a few light-years to hundreds. This suggested that the universe was not a uniform expanse but a complex structure, with stars clustered and scattered in patterns that hinted at larger forces at work. Gravity, motion, the history of star formation, all of these left their marks in the data. As the catalogue of stellar distances grew, astronomers began to see connections. Stars with similar colours and brightnesses tended to have similar distances. This allowed them to develop new methods for estimating distances to stars too far away for parallax. By comparing the apparent brightness of a distant star to the known brightness of similar nearby stars, they could infer how far away it was. These techniques, called standard candles, extended the reach of measurement far beyond parallax, eventually allowing astronomers to measure distances across the galaxy. The data from parallax measurements also provided a foundation for understanding stellar properties. If you know how far away a star is and how bright it appears, you can calculate its true luminosity, how much light it actually emits. This revealed that stars come in a vast range of sizes and powers. Some, like red dwarfs, are faint and cool, barely glowing. Others, like blue giants, are brilliant and hot, shining with the light of thousands of suns. The diversity of stars became clear only after their distances were known. Recording the data was painstaking work. Each observation had to be logged, each measurement cross-checked, each source of error accounted for. Astronomers filled notebooks with columns of numbers, angles, times, atmospheric conditions. They compared observations from different nights, different seasons, different years. They used mathematics to average out random errors, to identify systematic biases, to extract the true signal from the noise. The process was slow, methodical, and demanding, but it was also deeply satisfying. Each number added to the growing map of the stars. Think about what it means to hold a piece of data that describes the distance to a star. It is not just a number, it is a connection, a thread linking your mind to a distant sun separated from you by trillions of kilometers and years of travel time for light. The data transforms the star from a vague point in the sky into a real object with a position, a distance, a history. It makes the universe tangible in a way that speculation never could. The data also humbled those who gathered it. The nearest star was over 4 light-years away, meaning that even travelling at the speed of our fastest spacecraft, it would take tens of thousands of years to reach. The galaxy itself, they would later learn, was 100,000 light-years across. The distances revealed by parallax were just the beginning, a first step into a cosmos far larger than anyone had imagined. Each measurement pushed the horizon of the known outward, revealing more and more of the immensity beyond. For us today, the data collected by Bessel and his contemporaries remains foundational. Modern telescopes have extended parallax measurements to millions of stars, mapping the Milky Way in exquisite detail. Space missions like Gaia have measured parallaxes with unprecedented precision, refining our understanding of stellar distances and motions. But the principle remains the same. Observe carefully, measure precisely, record faithfully. The data tells the story, and the story is one of a universe far larger and more complex than we ever dared to imagine. Once astronomers had measured the distances to nearby stars, a new question emerged. If individual stars could be measured, what about the faint smudges of light that telescopes revealed in various parts of the sky? These nebulae, as they were called, appeared cloud-like, fuzzy and indistinct. Some thought they were clouds of gas within our own galaxy. Others suspected they might be something else entirely, perhaps distant collections of stars so far away that individual points of light blurred together into a haze. The debate over the nature of nebulae became one of the great mysteries of early 20th century astronomy. Some nebulae clearly were clouds of gas, glowing from the light of nearby stars. The Orion Nebula, for example, was close enough to show structure, swirls of gas and dust illuminated by young hot stars. But other nebulae, especially the spiral ones, looked different. They had distinct shapes, arms curving outward from a bright centre, and they seemed to rotate. Were they smaller structures within the Milky Way, or were they galaxies in their own right, entire systems of billions of stars lying far beyond our own? The question could not be answered by visual inspection alone. Distances had to be measured, and the techniques that worked for nearby stars did not reach far enough. Parallax became useless beyond a few hundred light-years. Standard candles, stars with known brightness, could extend the range, but only if such stars could be identified in the nebulae. The breakthrough came from an unexpected source, a type of star called a Cepheid variable. Cepheid variables are stars that pulsate, growing brighter and dimmer in a regular cycle. Henrietta Leavitt, working at the Harvard Observatory, discovered a remarkable relationship. The period of a Cepheid's pulsation, how long it takes to complete one cycle, is directly related to its intrinsic brightness. A Cepheid that pulsates slowly is more luminous than one that pulsates quickly. This meant that by measuring the period, you could determine the star's true brightness, and by comparing that to how bright it appeared, you could calculate its distance. Edwin Hubble, using the most powerful telescope of his time, the 100-inch reflector on Mount Wilson, searched for Cepheids in the Andromeda Nebula. He found them, faint but unmistakable, pulsating with regular periods. He measured those periods, calculated their true brightness, and then compared that to their apparent brightness. The result was stunning. Andromeda was not within the Milky Way. It was far beyond it. More than 2 million light-years away. It was not a nebula but a galaxy, a system of hundreds of billions of stars, comparable in size to our own. The discovery transformed everything. If Andromeda was a galaxy, then so were the other spiral nebulae. The universe was not just the Milky Way but a vast expanse filled with countless galaxies, each separated by millions of light-years. The scale of the cosmos expanded by orders of magnitude in a single stroke. What had seemed like the entire universe turned out to be just one galaxy among many. The deeper mystery was not how big the Milky Way was, but how big the universe of galaxies truly stretched. Hubble's work did not stop there. He measured the distances to more galaxies. Charting their positions and motions, he noticed something extraordinary. The farther away a galaxy was, the faster it appeared to be moving away from us. The light from distant galaxies was shifted toward the red end of the spectrum, a sign that they were receding. This redshift, as it came to be known, suggested that the universe itself was expanding, that space was stretching, carrying galaxies apart. This was the deeper mystery beneath the measurement of distances. The universe was not static but dynamic, growing, evolving. The galaxies were not fixed in place but drifting apart, carried by the expansion of space itself. The implications were profound. If the universe was expanding now, then at some point in the past, it must have been much smaller. Extrapolating backward led to the idea of a beginning, a moment when all of space, all of matter, all of energy was compressed into a tiny, hot, dense state. The Big Bang, as it would later be called. The deeper mystery revealed itself in layers. First, the stars were distant. Then, the galaxies were distant. Then, the universe itself was expanding. Each discovery opened onto another, each layer of understanding revealing a larger and stranger reality. The measurements that began with stellar parallax now extended to the edges of the observable universe. Distances measured not in light-years but in billions of light-years, scales so vast that they stretch the imagination to its limits. For us, the deeper mystery is both humbling and inspiring. It shows that the universe is not a simple place but a complex, dynamic, and ever-unfolding one. Every answer leads to new questions. Every measurement reveals new horizons. The act of looking outward is an act of discovery, and the discoveries never end. The deeper you look, the more there is to see, and the more you see, the more you realize how much remains unknown. The realization that the universe was expanding changed everything. It was not just a new piece of data, or a refinement of existing theories. It was a complete overthrow of the old paradigm, a shift so fundamental that it redefined humanity's understanding of the cosmos. For centuries, the universe had been imagined as eternal and unchanging, a vast stage on which events unfolded but which itself remained constant. The idea that space itself could grow, that the fabric of reality was dynamic, was almost incomprehensible. Edwin Hubble's observations of galaxy redshifts provided the evidence. The farther away a galaxy was, the faster it appeared to recede. This relationship, now known as Hubble's law, was not random. It was systematic, predictable, and profound. It suggested that the universe was not a static container, but an expanding one, growing in all directions at once. Every galaxy was moving away from every other galaxy, not because they were flying through space, but because space itself was stretching between them. The implications hit like a thunderclap. If the universe was expanding, then it must have been smaller in the past. Wind the clock backward far enough, and you arrive at a moment when all the matter and energy in the universe was concentrated in an incredibly hot, incredibly dense state. This was the beginning, the origin of everything, the moment that would later be called the Big Bang. The universe had a history, a narrative arc stretching from a singular beginning to the present and onward into an uncertain future. The paradigm shift was not immediate. Many scientists resisted the idea. Some, like Albert Einstein, had assumed the universe was static and had even introduced a cosmological constant into his equations to keep it from collapsing. When Hubble's data showed that the universe was expanding, Einstein called it his greatest blunder. Others proposed alternative explanations, suggesting that the red shift might be caused by something other than expansion. But as more data accumulated, the evidence became overwhelming. The universe was expanding, and there was no going back to the old static model. The shift in thinking extended beyond the technical. It changed how people saw their place in the cosmos. If the universe had a beginning, then it also had an age. It was not infinitely old, but finite in time, around 13.8 billion years. That meant everything we see, every galaxy, every star, every atom, came from that initial moment. The elements in our bodies, the light from distant stars, the structure of space itself, all of it traced back to the Big Bang. We were not separate from the universe, but woven into its very fabric. The paradigm shift also opened new questions. What caused the Big Bang? What existed before it, if anything? Will the universe expand forever? Or will it eventually collapse back on itself? These questions remain at the forefront of cosmology today, driving research and inspiring new theories. But the shift itself, the move from a static to a dynamic universe, was the foundation. Without that change in perspective, none of the later discoveries would have been possible. For astronomers, the expanding universe provided a new framework for understanding the cosmos. Distances could be measured not just in space but in time. Light from distant galaxies showed us the universe as it was, billions of years ago, younger, denser, hotter. By studying galaxies at different distances, astronomers could reconstruct the history of the universe, watching it evolve from the chaos of the early moments to the structured cosmos we see today. The paradigm shift also brought a new kind of humility. If the universe had a beginning, then it was not eternal in the way people had once imagined. It had a history, and that history was finite. We lived at a particular moment in that history, neither at the beginning nor at the end, but somewhere in the middle. The universe would continue long after humanity was gone, expanding, cooling, perhaps even fading into darkness as stars burned out and galaxies drifted beyond the reach of light. But there was also comfort in the shift. If the universe had a beginning, then it was comprehensible in a way that an eternal, unchanging cosmos was not. It had a story that could be told, a sequence of events that could be traced, a structure that could be mapped. The expanding universe was not a random or chaotic place, but one governed by laws, shaped by forces, filled with patterns that could be understood. The paradigm shift from static to dynamic, from eternal to finite, from unchanging to expanding, was perhaps the most important intellectual revolution in the history of astronomy. It reframed every question, redefined every scale, and opened the door to understanding the universe not just as a place, but as a process, an unfolding story in which we are both observers and participants. That shift continues to guide us today as we look outward and ask how big the universe truly is. The discovery that the universe was expanding sent ripples through the scientific community and beyond. It was not just astronomers who felt the impact. Physicists, philosophers, theologians, and ordinary people all grappled with what it meant. If the universe had a beginning, if space itself was growing, then the old certainties no longer held. The cosmos was not a fixed stage, but a living, evolving system. The immediate ripple of this realization touched every corner of thought. One of the first consequences was the development of the Big Bang theory. If the universe was expanding now, then extrapolating backward led to a singular point, a moment of origin. Georges Lemaitre, a Belgian priest and physicist, was one of the first to propose this idea, calling it the primeval atom. He imagined the entire universe compressed into a single point, which then exploded outward, creating space, time, matter, and energy all at once. It was a radical idea, but it fit the observations. The Big Bang theory predicted certain things that could be tested. One was that the universe should have cooled as it expanded. In the earliest moments, it would have been unimaginably hot, a plasma of particles and radiation. As space grew, temperatures dropped, allowing atoms to form. The theory predicted that remnants of this early heat should still be detectable, a faint glow filling the entire sky. This prediction seemed almost fantastical, but it turned out to be true. In 1965, Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background, a faint radiation coming from all directions, exactly as the Big Bang theory predicted. This discovery was one of the immediate ripples of the expanding universe idea. It confirmed that the cosmos had a history, that it had evolved from a hot, dense state to the cooler, more structured universe we see today. The cosmic microwave background became one of the most important pieces of evidence for the Big Bang, a snapshot of the universe when it was just 380,000 years old, still glowing from its own heat. Another ripple was the realization that the universe had an age. If you could measure how fast the universe was expanding, you could calculate when the expansion began. Early estimates placed the age at a few billion years, which created a problem because some stars seemed older than that. But as measurements improved, the age was revised upward. Today, we know the universe is approximately 13.8 billion years old. That number is not arbitrary. It is derived from careful observations of the expansion rate, the density of matter, and the properties of the cosmic microwave background. The immediate ripple also affected how people thought about time itself. If the universe had a beginning, then time had a beginning too. Before the Big Bang, there was no before. Time, like space, was created in that initial moment. This idea challenged intuition. We are used to thinking of time as an infinite backdrop, something that has always existed and always will. But the Big Bang suggested that time was part of the universe, not separate from it. The concept was difficult to grasp, but it reshaped philosophy and cosmology alike. In the decades following the discovery of expansion, scientists raced to understand the implications. How did galaxies form? How did stars ignite? How did the elements that make up planets and life come into existence? Each question led to new research, new observations, new theories. The expanding universe became the framework within which all of cosmology developed. Every discovery about the early universe, about the formation of structures, about the fate of the cosmos, traced back to that initial insight. The ripple also reached popular culture. The idea of a universe with a beginning captured imaginations. Books, films, documentaries explored the concept, bringing the story of the cosmos to a wider audience. People who had never looked through a telescope began to understand that they were part of something vast and ancient, a story that began billions of years ago and continues to unfold. The expanding universe was not just a scientific fact, but a narrative, a way of understanding our place in time. For scientists, the immediate ripple meant new tools, new techniques, new questions. Telescopes were built to study the cosmic microwave background in detail, mapping its tiny fluctuations. Particle accelerators were designed to recreate the conditions of the early universe, to understand the physics of extreme temperatures and densities. Computer simulations modeled the growth of structures, showing how the smooth early universe gave rise to the galaxies and clusters we see today. Each of these efforts was a direct consequence of the paradigm shift from static to dynamic. The immediate ripple also brought uncertainty. If the universe was expanding, what drove that expansion? Was it simply the momentum of the Big Bang? Or was there something else at play? Observations in the late 20th century suggested that the expansion was not just continuing but accelerating. driven by a mysterious force called dark energy. This discovery added another layer to the mystery, another ripple extending outward from the initial realization that the universe was not static. For us, thinking about the immediate ripple is a reminder of how one insight can transform everything. The discovery that the universe was expanding did not just answer a question. It opened a floodgate of new questions, new possibilities, new ways of seeing. It showed that the cosmos is not a finished product, but a work in progress, still revealing its secrets, still evolving, still surprising us. The immediate ripple continues today, every time a new telescope captures an ancient photon, every time a new measurement refines our understanding, every time we look outward and see the universe not as it is, but as it was. Unfolding across billions of years, the cosmic microwave background is the oldest light we can see, a faint glow that fills the entire sky. It is not the light of stars or galaxies, but the remnant radiation from the Big Bang itself, stretched and cooled by 13.8 billion years of cosmic expansion. When astronomers first detected it, they realized they were looking at an echo, a signal from the universe when it was just a newborn, still glowing from its own creation. This echo carries information about the early cosmos, about how structures formed, about the seeds that would eventually grow into galaxies, clusters, and the vast web of cosmic architecture we see today. To understand the cosmic microwave background, imagine the universe in its infancy. For the first few 100,000 years, space was filled with a hot, dense plasma of protons, electrons, and photons. The photons, particles of light, could not travel freely. They scattered constantly off the electrons, bouncing around in a thick fog. The universe was opaque, glowing but impenetrable. Light could not escape. It was trapped in the chaos of particles colliding and rebounding endlessly. Then, as the universe expanded and cooled, something remarkable happened. The temperature dropped enough for protons and electrons to combine into neutral hydrogen atoms. Suddenly, the photons were free. They no longer scattered off charged particles. They streamed outward in all directions, filling the universe with light. This moment, called recombination, marked the point when the cosmos became transparent. The photons released at that instant have been travelling ever since, and we see them today as the cosmic microwave background. But those photons have changed. When they were released, they were high energy, in the visible and ultraviolet range. Over billions of years, as space itself expanded, their wavelengths stretched. Today, they arrive as microwaves, invisible to the eye but detectable with specialized instruments. Stretching of the light is a direct consequence of cosmic expansion, a reminder that the universe has been growing all along, carrying those ancient photons across immense distances and immense time. What makes the cosmic microwave background so valuable is its uniformity. When you map it across the entire sky, it appears almost perfectly smooth, with a temperature of about 2.7 degrees above absolute zero. This uniformity tells us that the early universe was remarkably homogeneous, with matter and energy distributed almost evenly, but not perfectly evenly. There are tiny fluctuations, temperature differences of only a few millionths of a degree. These tiny variations are the seeds of everything that came later. Where the temperature was slightly higher, there was slightly more matter. Gravity, acting over millions and billions of years, pulled that extra matter together, forming the first stars, the first galaxies, the first clusters. The tiny ripples in the cosmic microwave background are the blueprints of the universe's structure. By studying them, astronomers can trace the origins of galaxies, understand how matter clumped together, and test theories of cosmic evolution. The discovery of the cosmic microwave background was accidental. In 1965, Arno Penzias and Robert Wilson were testing a sensitive radio antenna in New Jersey. They detected a persistent noise, a faint hiss coming from all directions. They checked for interference, cleaned pigeon droppings from the antenna, eliminated every possible source of error. But the noise remained. It was only when they consulted with cosmologists that they realized what they had found. The hiss was the echo of the Big Bang, the oldest light in the universe, arriving as a whisper from the past. Their discovery confirmed the Big Bang theory, and earned them the Nobel Prize. But more importantly, it opened a new window into the early universe. Telescopes designed to study the cosmic microwave background have mapped its fluctuations in exquisite detail. Missions like COBE, WMAP, and Planck have charted the temperature variations across the sky, revealing the structure of the universe when it was just a fraction of its current age. These maps are some of the most important images in cosmology, capturing the universe in its infancy, before galaxies, before stars, when everything was potential waiting to unfold. The echoes through time tell us more than just the story of the early universe. They also constrain the universe's composition. By analysing the patterns in the cosmic microwave background, scientists have determined that ordinary matter, the stuff of stars and planets, makes up only about 5% of the universe's total energy. Another 27% is dark matter, invisible but detectable through its gravitational effects. The remaining 68% is dark energy, a mysterious force driving the accelerated expansion of space. These numbers come from studying the echoes, from measuring the ripples in the ancient light. Think about what it means to see light from the moment the universe became transparent. It is like looking at a photograph of a newborn, seeing the features that will define it for the rest of its life. The cosmic microwave background is that photograph, and the features are the seeds of galaxies, the hints of structure, the promise of everything that would come later. By studying it, we connect with the earliest moments of cosmic history, bridging 13.8 billion years in a single observation. The echoes also remind us of how interconnected everything is. The light we see today left the surface of last scattering when the universe was 380,000 years old. It has been travelling ever since, crossing billions of light years, arriving now at our telescopes. In that journey, it has witnessed the formation of the first stars, the birth of galaxies, the clustering of matter into filaments and voids. It has seen the universe grow, cool, and structure itself. And now, it arrives here, carrying with it the memory of the beginning. For us, the cosmic microwave background is both a gift and a mystery. It is a gift because it provides a window into the past, a way to test theories, a tool for understanding how the universe evolved. It is a mystery because it also reveals how much we do not know. Why were the initial fluctuations so small? What caused them? What happened in the first fractions of a second before the universe became transparent? These questions remain, and the echoes, for all their richness, do not answer everything, but that is part of the wonder. The cosmic microwave background is a reminder that the universe has a story, that it began in a moment of unimaginable heat and density, and that it has been growing and evolving ever since. The echoes through time are not just data points but connections, threads linking the present to the past, linking us to the earliest moments of creation. By listening to those echoes, we hear the voice of the universe itself, speaking across billions of years, telling the story of how everything came to be. Behind every measurement, every theory, every discovery about the size and structure of the universe, there are people, not just institutions or instruments, but individual minds, driven by curiosity, determination, and a willingness to dream of answers to questions that seemed impossible. These dreamers are the astronomers, physicists, and thinkers who refused to accept that the cosmos was unknowable, who built careers around pushing the boundaries of measurement, who spent lifetimes chasing faint signals from the edges of the observable universe. Their names are not always famous, but their contributions are woven into the fabric of what we know today. Consider Vera Rubin, an astronomer who spent decades studying the rotation of galaxies. She measured how fast stars moved at different distances from galactic centers, expecting to find that stars farther out moved more slowly, just as planets farther from the sun orbit more slowly. But she found the opposite. Stars at the edges of galaxies moved just as fast as those near the center, sometimes even faster. This was impossible unless there was more mass in the galaxies than could be seen. She had discovered evidence for dark matter, invisible material that outweighs visible matter by a factor of 5 or more. Her work revealed that most of the universe's mass is hidden, shaping galaxies from the shadows. Rubin's discovery was not accepted immediately. Some dismissed it as error, others as an anomaly. But she persisted, gathering more data, refining her methods, showing that the pattern held for galaxy after galaxy. Eventually, the evidence became undeniable. Dark matter was real, and it changed everything. Without it, galaxies would fly apart. Without it, the structures we see today would never have formed. Rubin did not just measure rotations, she uncovered a fundamental truth about the cosmos. Then there is Henrietta Leavitt, whose work on Cepheid variables provided the key to measuring distances across the universe. Working at the Harvard Observatory in the early 20th century, Leavitt analysed thousands of photographic plates, measuring the brightness of stars in the Magellanic Clouds. She noticed that certain stars, the Cepheids, pulsated with regular periods and that the period was related to their brightness. Brighter Cepheids pulsated more slowly, fainter ones pulsated faster. This relationship became the foundation for measuring cosmic distances, allowing astronomers like Edwin Hubble to determine that galaxies lay far beyond the Milky Way. Leavitt's contribution was profound, yet she received little recognition during her lifetime. She worked in an era when women were often relegated to the role of computers, performing calculations and measurements for male astronomers. Despite these barriers, her discovery transformed cosmology. Every distance measured using Cepheids, every map of the universe's structure, every estimate of cosmic scale, traces back to her patient observation of variable stars. She dreamed of understanding the stars, and in doing so, she gave humanity the tools to measure the universe. Then there are the theorists, people like George Gamow, who imagined what the early universe must have been like. Gamow, working in the mid-20th century, calculated that if the universe began in a hot, dense state, it should have produced specific amounts of hydrogen, helium, and other light elements. His predictions matched observations, providing strong support for the Big Bang theory. He also predicted that remnants of the early heat should still be detectable, an idea that led to the discovery of the cosmic microwave background. Gamow dreamed of a universe with a history, and his calculations helped prove it. There are also the dreamers who built the instruments. Engineers who designed telescopes, spectrographs, detectors, each one pushing the limits of what was possible. The construction of the 100-inch telescope on Mount Wilson, the largest in the world for decades, required years of labour and innovation. The design of the Hubble Space Telescope, orbiting above the atmosphere to capture clearer images than any ground-based instrument, took the collaboration of thousands of people. Each of these projects was driven by the dream of seeing farther, measuring more precisely, understanding more deeply. And then there are the dreamers whose names we do not know, the assistants who performed calculations, the technicians who calibrated instruments, the observers who spent cold nights at telescopes recording data. Each played a role, each contributed to the collective effort. Science is not the work of solitary geniuses, but of communities. Generations of people building on each other's efforts, sharing ideas, refining methods, correcting errors. The dreamers are not just individuals but networks, connected across time and space by the shared goal of understanding the cosmos. What unites all these dreamers is a willingness to ask questions that seem too large, to pursue answers that seem too distant. They work with incomplete data, imperfect instruments, and theories that are always provisional. They face skepticism, resistance, failure, but they keep going because the dream of understanding the universe is more powerful than the obstacles. They believe that the cosmos, vast as it is, can be known, and that belief drives them forward. For us, thinking about the dreamers is a reminder that the universe does not reveal its secrets easily. It takes patience, persistence, and imagination. It takes people willing to spend decades on a single problem, willing to fail and try again, willing to challenge assumptions and embrace uncertainty. The dreamers show us that understanding the size of the universe is not just a technical achievement but a human one, shaped by the same qualities that drive all great endeavours: curiosity, courage, and hope. The dreamers also remind us that the work is never finished. Each discovery opens new questions. Each measurement reveals new mysteries. The size of the universe may be approximately 93 billion light-years across in its observable extent, but beyond that, we do not know. The dreamers of today are mapping dark matter, studying dark energy, searching for gravitational waves, probing the earliest moments of cosmic history. They are building new telescopes, developing new theories, asking new questions, and future dreamers will continue the work, pushing the boundaries farther, measuring deeper, understanding more. The dreamers are the heartbeat of cosmology. The human element in a field that deals with the largest scales imaginable. They remind us that behind every number, every graph, every image of the cosmos, there are people who cared, enough to look, to measure, to dream. And because they did, we now know more about the universe than ever before. Not just its size, but its history, its structure, its fate. The dreamers gave us that knowledge, and they continue to give it, one observation at a time, one calculation at a time, one question at a time. Science is often portrayed as a smooth path from ignorance to knowledge, a steady accumulation of facts building towards certainty. But the reality is messier. Understanding the size of the universe has been a battle, not in the sense of violence, but in the sense of struggle, disagreement, and competing interpretations. Different measurements have given different results. Different methods have pointed in different directions, and the tension between these approaches, the battle for truth, continues today, reminding us that even well-established ideas remain subject to refinement and challenge. One of the most significant ongoing tensions involves the rate of cosmic expansion, known as the Hubble constant. This number tells us how fast the universe is growing, how quickly galaxies are moving apart. If you know the Hubble constant precisely, you can calculate the age of the universe, its size, and its future. But different methods for measuring the Hubble constant have produced different values, and the discrepancy has persisted despite improvements in technology and technique. One approach uses the cosmic microwave background, the ancient light from the early universe. By analysing its tiny fluctuations, cosmologists can infer the expansion rate at that time and extrapolate forward to the present. This method, refined by missions like the Planck satellite, suggests a Hubble constant of around 67 kilometers per second per megaparsec. In simpler terms, for every megaparsec, about 3.26 million light-years of distance, space is expanding at 67 kilometers per second. But another approach, using observations of nearby galaxies and Cepheid variables, gives a different answer. By measuring distances to galaxies and their velocities, astronomers can directly calculate the expansion rate. This method, championed by teams using the Hubble Space Telescope, suggests a higher value, around 73 kilometers per second per megaparsec. The difference might seem small, but it is significant enough that it cannot be explained by random error. Something is off, and no one is sure what. This discrepancy has been called the Hubble tension, and it has sparked a battle for truth. Both methods are rigorous, both teams are experienced, and both results have been checked and rechecked, yet they do not agree. Some scientists suspect there is a flaw in one of the methods, a systematic error that has not been identified. Others wonder if the tension points to new physics, something not accounted for in current models. Perhaps dark energy behaves differently than expected. Perhaps the expansion rate has changed over time in ways we do not fully understand. The battle is not personal but scientific, a clash of evidence that demands resolution. Another battle involves the measurement of cosmic distances more generally. Different techniques, from parallax to Cepheids to supernovae to gravitational lensing, all provide ways to estimate how far away objects are. But each method has uncertainties, and each builds on the previous one, creating a distance ladder where errors can accumulate. If one rung is off, the entire ladder shifts. Astronomers work constantly to cross-check measurements, to calibrate methods, to ensure that the distances they report are reliable. But the battle is ongoing, a continuous effort to refine, improve, and verify. The battle for truth also extends to the nature of dark energy. Observations suggest that the expansion of the universe is accelerating, driven by some mysterious force. This discovery, made in the late 1990s, was so unexpected that it initially met with skepticism. How could the universe be speeding up? What could drive that acceleration? Dark energy, as it was named, became the leading explanation, but its nature remains unknown. Is it a property of space itself, a cosmological constant as Einstein once proposed, or is it something more dynamic, changing over time? Different observations give different hints, and the battle to understand dark energy continues. These battles are not failures. They are the engine of progress. Science advances not by everyone agreeing, but by people questioning, testing, and challenging. The tension between different measurements forces researchers to look more carefully, to refine their instruments, to develop new techniques. It keeps the field honest, preventing complacency, ensuring that conclusions are based on solid evidence rather than assumption. For us, the battle for truth is a reminder that knowledge is provisional. What we know about the size of the universe is based on the best available evidence, but that evidence is always subject to revision. New telescopes might reveal new information. New theories might reinterpret old data. The universe itself does not change, but our understanding of it evolves, shaped by the ongoing struggle to measure accurately and interpret correctly. The battle also shows that science is a collective endeavour. No single person holds the truth. Different teams work on different pieces of the puzzle, and sometimes their pieces do not fit together neatly. When that happens, the community comes together to investigate, to debate, to find the source of the disagreement. It is a process that can be slow and frustrating, but it is also the only reliable way to approach questions as large as the size of the universe. In the end, the battle for truth is not about winning or losing, but about getting closer to reality. Each measurement, each refinement, each new method brings us a step nearer to understanding how big the universe truly is. The tension between different results is not a weakness but a strength, a sign that the field is alive, active, and deeply engaged with the most fundamental questions about the cosmos. The battle continues, and that is exactly as it should be. As measurements improved and theories refined, a startling realization emerged. The universe we can see, the galaxies, stars, and planets, the nebulae and clusters, all the light and matter we have ever detected, makes up only a tiny fraction of what exists. The rest is invisible, hidden from our telescopes, detectable only through its gravitational effects. This new awareness changed everything. It revealed that the cosmos is not what it appears to be, that most of the universe is made of things we cannot see, and that our understanding is based on observing only the luminous tip of a much larger reality. The first hint came from the study of galaxy rotation, the work of astronomers like Vera Rubin and others. Stars at the edges of galaxies move too fast. Without some unseen mass holding them in place, they should have been flung into space by their own momentum. The only explanation was that galaxies contained far more matter than the visible stars, gas, and dust. This invisible matter, called dark matter, does not emit, absorb, or reflect light. It interacts only through gravity. It forms massive halos around galaxies, invisible but essential, providing the scaffolding on which visible matter is arranged. As astronomers map the distribution of galaxies, they realize that dark matter is not confined to individual galaxies. It permeates the universe, shaping the cosmic web, guiding the formation of clusters and filaments. Computer simulations that included dark matter could reproduce the large-scale structure we observe. Simulations without it could not. The invisible mass was not a curiosity, but a foundation. Without dark matter, galaxies would not have formed, clusters would not have assembled. The universe as we know it would not exist. But dark matter was only part of the story. In the late 1990s, observations of distant supernovae revealed something even stranger. The expansion of the universe was not slowing down, as gravity should have caused, but speeding up. Something was pushing space apart, overcoming the pull of gravity, accelerating the growth of the cosmos. This force, named dark energy, is even more mysterious than dark matter. It does not clump like matter. It does not interact with particles. It seems to be a property of space itself, a kind of energy that becomes stronger as the universe grows. The implications are staggering. Calculations suggest that dark energy makes up about 68% of the universe's total energy. Dark matter accounts for another 27%. Ordinary matter, everything we can see, touch, or measure directly, is only about 5%. That means 95% of the universe is invisible to us, made of things we do not fully understand. This new awareness reshaped cosmology, turning it from the study of visible structures to the study of invisible forces. Think about what that means. When you look at the night sky, you are seeing only a sliver of reality. The stars, galaxies, and nebulae are the exception, not the rule. Most of the universe is dark, not because it is far away or hidden behind dust, but because it does not emit light. It is made of particles that do not interact with photons, fields that do not couple with matter in the familiar ways. The universe is not a collection of glowing objects scattered through empty space. It is a complex, layered structure where the invisible dominates, and the visible is a rare and precious exception. The new awareness also brought humility. For centuries, humans assumed that what we could see was most of what existed. Improving telescopes revealed more stars, more galaxies, more structures, but the assumption remained that visibility equated to reality. Dark matter and dark energy shattered that assumption. They showed that our senses, even enhanced by instruments, capture only a fraction of the whole. The universe is richer, stranger, and more complex than we imagined. But the new awareness also brought wonder. If 95% of the universe is invisible, then we live in a cosmos far more mysterious than we thought. Every galaxy we see is embedded in a halo of dark matter. Every cluster is shaped by forces we cannot directly observe. Every expansion of space is driven by energy we cannot isolate. The visible universe is like the foam on the surface of the ocean, a thin layer floating on something vast and deep. To understand the cosmos, we must learn to see what is not visible, to infer the invisible through its effects, to build theories that account for what cannot be directly measured. Scientists have proposed various candidates for dark matter. Perhaps it is made of exotic particles, remnants from the early universe, drifting through space in vast clouds. Perhaps it is something even stranger, a consequence of modified gravity, a sign that our understanding of physics is incomplete. Experiments search for dark matter particles, deep underground to shield from cosmic rays, waiting for the rare collision that might reveal their presence. So far, none have been definitively detected, and the mystery deepens. Dark energy is even more elusive. Some theories suggest it is the cosmological constant, a fixed energy inherent in space itself. Others propose that it is dynamic, changing over time, driven by fields or particles we have not yet discovered. The acceleration of the universe, driven by dark energy, suggests a future where galaxies drift farther and farther apart, where the cosmic horizon expands but becomes emptier, where the night sky grows darker as distant galaxies recede beyond the reach of light. This future is billions of years away, but it is a consequence of the invisible forces at work today. The new awareness of dark matter and dark energy is not the end of the story. It is a beginning, a recognition that the universe holds secrets we are only starting to uncover. Each discovery reveals how much remains unknown, how much of the cosmos is hidden from our direct perception. But that is not a cause for despair. It is a cause for wonder, for curiosity, for the determination to keep searching, to keep measuring, to keep asking questions even when the answers seem impossibly distant. For us, the new awareness is a reminder that the universe is not finished revealing itself. What we know is only a fraction of what exists. What we see is only a fraction of what is there, and yet, from that small fraction, we can infer the rest, using gravity as a lens, using mathematics as a guide, using the human capacity for imagination and reason to reach beyond the visible and touch the invisible. That is the power of science, and that is the gift of the new awareness. It shows us a universe vaster and stranger than we could have imagined, and it invites us to keep exploring, to keep learning, to keep expanding our understanding of the cosmos in all its hidden complexity. After all the measurements, all the theories, all the refinements and debates, a number emerges. The observable universe is approximately 93 billion light-years in diameter. That figure is not speculative, It is derived from careful observation of the cosmic microwave background, the expansion rate of space, the distribution of galaxies, and the age of the universe. It represents the farthest distance from which light could have reached us since the Big Bang, accounting for the expansion of space during the time that light was travelling. It is the deepest truth we have about the size of the cosmos, at least the part we can see. But even this number comes with caveats. The observable universe is not the entire universe. It is only the region from which light has had time to reach us. Beyond that horizon, the universe continues, perhaps infinitely, perhaps not. We cannot know. The cosmic horizon is not a wall but a limit of information, a boundary beyond which signals have not yet arrived and may never arrive. The universe beyond our horizon may be identical to what we see, filled with galaxies and clusters, or it may be entirely different. We have no way of knowing because we cannot observe it. The deepest truth is that the universe is larger than we can measure. The 93 billion light-years represents only the bubble of visibility centered on us. Every observer in the universe has their own bubble, their own horizon, their own observable slice. The bubbles overlap, but they are not the same. An observer in a galaxy billions of light-years away would see galaxies we cannot, and they would miss galaxies we can see. The total universe, the sum of all bubbles, may be infinite, or it may have a finite but unimaginably large size. We do not know, and we may never know. This uncertainty is not a failure of science. It is a recognition of limits. There are things we can measure and things we cannot. The observable universe is within reach. The total universe, if it is infinite, is forever beyond. But even the observable slice is so vast that it challenges comprehension. 93 billion light-years means that light travelling at 300,000 kilometers per second takes 93 billion years to cross from one edge to the other. That is longer than the age of the universe, which seems paradoxical until you remember that space itself has been expanding all along, stretching the distances as the light travelled. To put 93 billion light-years in perspective, consider that the entire Milky Way, with its 100 billion stars, is only about 100,000 light-years across. You could line up 930,000 Milky Ways edge to edge to span the observable universe. Or think of it another way. If the Milky Way were the size of a coin, the observable universe would be a sphere several kilometers wide. The scale defies everyday experience, but that is the reality we inhabit. The deepest truth also includes what we know about the contents of this vast expanse. Within the observable universe, there are approximately 2 trillion galaxies, each with hundreds of billions of stars. That means the number of stars in the observable universe is on the order of 10 to the 24th power, a 1 followed by 24 zeros. It is more stars than grains of sand on all the beaches of Earth, and each star may have planets, and each planet is a world, and the sheer abundance is overwhelming. The observable universe is not empty, it is full, teeming with structures at every scale, but the deepest truth is not just about size or quantity. It is also about what this immensity means. It means that we are part of something vastly larger than ourselves, something that stretches across billions of light years and billions of years of time. It means that our planet, our solar system, our galaxy, are tiny in the cosmic scale, yet they are also part of the whole. There is no centre to the observable universe. Every point is equally valid. Every observer sees themselves at the centre of their own horizon. In that sense, we are both insignificant and central, both lost in the vastness and connected to it. The deepest truth also points to the future. The universe is not static, it is expanding, and that expansion is accelerating. In billions of years, distant galaxies will move beyond our cosmic horizon, disappearing from view as space stretches faster than light can travel. The observable universe will grow in size but become emptier, with fewer galaxies visible. Eventually, in the far future, observers in our galaxy may see only the local group of galaxies, with the rest of the cosmos receded beyond reach. The universe will still be vast, but it will seem smaller, lonelier. And yet, even knowing this, the the deepest truth remains one of connection. The light we see from distant galaxies is ancient, emitted billions of years ago when the universe was younger. We are not seeing those galaxies as they are now, but as they were. The observable universe is a patchwork of different times, different ages, all layered together in a single view. Every photon that reaches us is a messenger from the past, carrying with it the history of its journey. By studying those photons, we learn not just about the size of the universe, but about its story, its evolution, its transformation, from a hot, dense beginning to the structured cosmos we see today. The deepest truth is humbling and inspiring in equal measure. It tells us that the universe is larger than we can fully grasp, but it also tells us that we are capable of measuring it, of understanding it, of placing ourselves within it. The 93 billion light-years is not just a number. It is a testament to human curiosity, to the generations of astronomers who built on each other's work, who refined their methods, who refused to accept that the cosmos was unknowable. They gave us this truth, this measure of the observable universe, and with it, a new way of seeing our place in the grand design. When you hold the number in your mind, 93 billion light-years, when you think about the trillions of galaxies, the incomprehensible number of stars, the vastness of space stretching in every direction, a question naturally arises. What does it all mean? Not in a technical sense, not in terms of measurements or theories, but in a deeper, more personal way. What does it mean for us, small beings on a small planet, to exist in a universe this large? How should we feel about our place in such immensity? There is no single answer. Different people, different cultures, different philosophies have pondered this question and arrived at different conclusions. Some find the vastness humbling, a reminder of how small we are, how brief our lives, how insignificant our concerns in the face of cosmic time and space. Others find it inspiring, a reminder that even in our smallness, we are part of something grand, something beautiful, something worthy of awe. Both responses are valid. Both are part of the human experience of confronting scale. One way to think about it is through the lens of connection. Yes, we are small. Our planet is a speck in a galaxy that is one among trillions. Our lives are fleeting compared to the billions of years the universe has existed. But we are also made of the universe. The atoms in our bodies were forged in stars, scattered by supernovae, gathered into clouds of gas and dust, and eventually incorporated into the Earth. We are not separate from the cosmos. We are part of it, woven into its fabric, shaped by its history. That connection suggests that our smallness is not a diminishment but a relationship. We are not outside the universe looking in. We are inside, participating, experiencing. The universe, through us, becomes aware of itself. Through human minds, the cosmos contemplates its own vastness. In that sense, we are not insignificant. We are the universe's way of knowing itself, and that is a profound role. Another way to ponder the meaning is through the lens of perspective. Knowing the size of the universe changes how we see our problems, our conflicts, our daily concerns. The things that feel overwhelming, the stresses and struggles of life, they do not disappear, but they are placed in context. We are on a small planet orbiting an ordinary star in an unremarkable part of one galaxy among trillions. Our worries, as real as they feel, are also temporary, local, and part of a much larger story. That perspective can be comforting. It reminds us that the universe is patient, that time is long, that the stars will continue to shine long after we are gone. But perspective can also be empowering. If we are small, then our lives are precious precisely because they are brief. Every moment becomes more valuable when placed against the vastness of cosmic time. Every connection we make, every act of kindness, every creation, every moment of wonder, they matter because they are ours, because they are part of the human experience within the larger universe. Smallness does not erase meaning. It concentrates it. Pondering the meaning also raises questions about life elsewhere. In a universe with trillions of galaxies, each with hundreds of billions of stars, many of which have planets, it seems unlikely that Earth is the only place where life has emerged. Statistical probability suggests that somewhere, perhaps in many places, Other beings are looking up at their own skies, asking the same questions we are. Are we alone? How big is the universe? What does it mean to exist? The vastness that makes us feel small also suggests that we might not be unique, that the cosmos might be filled with life, with intelligence, with other minds pondering the same mysteries. This possibility does not diminish us. If anything, it enriches the story. It suggests that the universe is not a barren expanse, but a place where complexity and awareness can arise, where matter can organize itself into forms capable of wonder. Whether we ever find evidence of other life or not, the possibility itself is part of what makes the universe meaningful. It reminds us that the cosmos is not just large, but generative, creative, capable of producing stars, planets, and perhaps minds like ours scattered across the vast expanse. Pondering the meaning also invites us to think about purpose. In a universe this large, what is our purpose? For some, the answer is survival, ensuring that humanity continues, spreads, explores. For others, it is understanding, using our minds to learn as much as we can about the cosmos. For still others, it is connection, building relationships, creating art, sharing experiences. There is no single purpose imposed by the universe. We create our own meanings, our own goals, our own reasons for being. And that freedom, that responsibility, is part of what makes existence precious. In the end, pondering the meaning of the universe's size is an act of philosophy as much as science. It is about taking what we know, the measurements, the distances, the structures, and asking what it implies for how we live, how we think, how we relate to each other and to the cosmos. The universe is vast, but it does not demand anything from us. It simply is. What we make of that vastness, how we respond to it, how we let it shape our sense of wonder and our sense of purpose, that is up to us. For now, as you drift toward rest, let the meaning settle gently. The universe is large, larger than we can fully comprehend, but you are part of it, connected to it through the very atoms of your being. Your life, brief as it is a moment in cosmic time, a flicker of awareness in the vastness. And in that moment, you are both everything and nothing, both infinitely small and infinitely significant. Let that paradox hold you, let it comfort you, let it remind you that you belong here, in this vast, mysterious, beautiful universe. We have travelled far, from the shadows measured in ancient cities to the cosmic microwave background glowing across the sky. From the distance to the nearest star to the edge of the observable universe. From the smallness of Earth to the vastness of galaxy clusters, filaments, and voids. The journey outward has been a journey through scale, through time, through the history of human understanding, and now, gently, we return. Not to a smaller world, but to a richer one. A world that is still small, but now understood as part of something infinitely larger. The legacy of measuring the universe is not just a collection of numbers. It is a way of seeing. It is the knowledge that when you look up at the stars, you are looking across light years, across millions or billions of years of time, across distances so vast they challenge the imagination. It is the awareness that the night sky is not a ceiling but a window. That every point of light is a world, a story, a connection to the larger cosmos. That legacy changes how we see ourselves, not as the centre of everything, but as participants in something grand. The legacy also lives in the tools and methods developed over centuries, from the geometry of Eratosthenes to the parallax measurements of Bessel, from the Cepheid variables of Leavitt to the redshifts measured by Hubble, each step built on the last. The cosmic distance ladder, with its rungs of parallax, standard candles, and expanding space, is a monument to human ingenuity. It shows that even when the universe seems beyond reach, persistence and creativity can find a way. But the legacy is not finished. The work continues. New telescopes peer deeper into space. New missions map the cosmos in greater detail. New theories attempt to explain dark matter and dark energy. The size of the universe, as we understand it today, is only the current answer, subject to refinement as better data arrives. Future generations will measure more precisely, understand more deeply, and perhaps discover that the universe is even larger, stranger, and more wonderful than we currently believe. And so we return, not to a place but to a feeling. The feeling of standing under the night sky, aware of the immensity above and around, aware of our small place within it, and yet also aware of our connection. The stars we see are part of us, and we are part of them. The elements in our bodies were forged in their cores. The light we see tonight left those stars years, centuries, millennia ago, travelling across the void to reach us now. We are both tiny and infinite, both fleeting and eternal, both separate and woven into the fabric of everything. The return is also a reminder that the question, what is the size of the universe, does not have a final answer. The observable universe is 93 billion light-years across, but beyond that, we do not know. The total universe may be infinite, or it may curve back on itself, or it may be one bubble in a multiverse. We may never know, but that uncertainty does not diminish what we have learned. It only adds to the mystery, to the sense that the cosmos is richer than we can imagine, that every answer opens onto new questions, that the journey of understanding never truly ends. As you settle into stillness, let the journey rest. You have travelled from Earth to the stars, from galaxies to clusters, from the observable universe to the edge of the knowable. You have seen the cosmos unfold across billions of light-years and billions of years of time. You have touched the infinite, not with your hands but with your mind, and that touch lingers. The universe is vast, but it is also here, present in the light that reaches your eyes, in the air you breathe, in the atoms of your body. The legacy of measuring the universe is a gift to all of us. It gives us a sense of scale, a way to understand where we are and what surrounds us. It humbles us by showing how small we are, and it elevates us by showing what we are capable of understanding. It reminds us that curiosity is one of the most powerful forces in the human experience, that the desire to know, to measure, to explore is what drives us to build telescopes, launch spacecraft, and ask questions that seem impossible. And so, we return, changed by the journey. The universe is the same as it was before, but we see it differently now. We know its size, or at least the size of the part we can see. We know its history, its structure, its composition. We know that it is expanding, that it began in a moment of unimaginable heat, that it will continue growing for eons to come. We know that most of it is invisible, that dark matter and dark energy shape the cosmos in ways we are only beginning to understand. We know that we are made of stardust, that our existence is a consequence of cosmic processes stretching back to the beginning. But more than knowledge, we carry with us a feeling, the feeling of awe, of wonder, of quiet connection to something larger than ourselves. The universe does not need us to understand it. It would continue just fine without our measurements, our telescopes, our theories. But we need to understand it. We need to look up, to ask how big, to trace the distances and ponder the meanings. That need is part of what makes us human, and the answers we find, partial and provisional as they are, enrich our lives in ways that cannot be measured. So let the legacy rest gently with you as you drift towards sleep. The stars will continue to shine, the galaxies will continue to turn, the universe will continue to expand, and somewhere in that vastness, on a small planet orbiting an ordinary star, you exist, aware of the immensity connected to it, part of it. The journey outward has brought us home, not to a smaller world, but to a richer one, a world that is still tiny in the cosmic scale, but also precious, unique, and filled with meaning. The size of the universe is vast beyond imagining, but you do not need to hold all of it at once. You only need to know that it is there, that you are part of it, and that the connection between the smallest and the largest, between the briefest and the eternal, is real. That connection is the deepest truth, the legacy that endures, the gift of understanding that humanity has earned through patience, curiosity, and wonder. And with that gift, you can rest, held by the universe itself, part of the infinite, forever at home. And so, we arrive at the quiet end of our journey through space and time. From shadows in Alexandria to the cosmic microwave background, from the nearest star to the edge of the observable universe, we've wandered through scales so immense they dissolve into wonder. The universe will keep expanding, stars will keep shining, galaxies will keep turning, whether we are watching or not. For now, all you need to do is rest. Thank you for joining me on this exploration, for letting curiosity guide you gently through the cosmos and towards sleep. If you found comfort here, I invite you to return whenever you'd like to drift through the stars at a softer pace. You can also support this journey by subscribing, so that more nights like this can follow. For now, let go of the numbers, let go of the distances, and let the vastness of the cosmos hold you like a blanket woven from starlight. Breathe slowly, and let the whisper of the infinite carry you into dreams. Good night.